Hello to everyone who's watching on YouTube. I'm just waiting for a few people to join the session in person. So I guess we'll get started in like 10 minutes to see if a few people join the session in person. Okay, so hi Samsung. Uh, uh, so we'll get started in like 5 to 10 minutes, like just waiting for a few more people to join the session. Okay, so it seems that no one has joined the session yet in person. So I'll just get started with it while addressing the or YouTube audience. So, hello to everyone who's watching on YouTube. Just to reintroduce myself, I'm Lakshay Saggi, the problem solving TA for the NPTEL Games and Information course. And this will be our 12th and last problem solving session, uh, at least for this semester, like NPTEL goes. And in this session, we'll be discussing problems related to correlated equilibrium, basically the topics which were taught in this week. So, yeah, again, like previous couple of weeks, a lot of theory was covered, and so mostly the problems will be theoretical in nature. And like previous times, I prepared a bunch of like quick summary notes so that we can like revise the concepts a bit before we get started with the theory based questions. And there are a couple of numerical questions also based on correlated equilibrium. And just to uh, just to remind everyone, so even though today is our last problem solving session, but tomorrow there will be a summary session, a 1 hour summary session from 6 to 7 p.m. And in that session, uh, I'll not be discussing any problems, but rather I'll be going over like the the high level concepts which were covered in the last 12 weeks. In the I'll be giving a quick overview, you can say, of the all the concepts which we covered in the course in the like last 12 weeks. So just to see how far we have come, and hopefully like it will act as a quick revision for you guys. So hopefully I'll see you guys tomorrow in that summary session also. But for now, let's just get started with the problems for today. So I'll just share my screen and then we can get started. Okay. I hope my screen is visible to everyone. So maybe I just zoom. Yeah. So again, like I said, we have a bit of like these are just screenshots from the lectures only, the high level concepts which were covered, the main concepts. I just took out these screenshots as a like, which can act as a quick revision notes for you guys also. And then we have a bunch of questions. So most questions are theoretical in nature, except one or two numericals. So, uh, like since no one has joined the session in person, I believe this won't be a very long session, since the theory covered was also pretty much not like, even though it was new, but it followed a lot of it followed from like previous weeks only. Like it was similar to the concepts covered in previous weeks. So yeah, I believe this session will get over a bit earlier than the previous sessions. So let's just get started with what was discussed first in this week. So uh, mainly the concept of correlated. Uh, the main concept which was covered in this week was actually correlated equilibrium, and everything else was just uh, different types of correlated equilibrium and stuff. So what does correlated equilibrium say? So last week we discussed problems where one can impose binding contracts on the player. So if a person can impose contracts which are binding on the players, and like if the players don't choose to sign those contracts, then also like they must do something, or like if they sign the contract they must do something else. So last week we discussed problems related to binding contracts, but this week we shift the focus to non-binding contracts. So non-binding contracts are something where like even though players are made aware of the contract, it doesn't mean that the player has to necessarily agree to do, like even though a player signs a contract, it doesn't mean that the player will actually play what the contract says. So suppose like in a game of two people, like let's say the contract says that if Alice signs a contract, then she has to play like up or something like that. But in non-binding contracts, even though Alice signs a contract, it doesn't really matter. Alice can actually play down also. It's not necessary for Alice to play up. So these are what are called non-binding contracts. So non-binding. So one might think like, what's even the use of these contracts? Like, if the contracts are non-binding, then they may as well not exist at all. Like, why are we even talking about non-binding contracts? Like, a contract means something which one has to do. So we talk about these non-binding contracts because these contracts are a way to facilitate communication between the players. So suppose there are two players, Alice and Bob, then these contracts are a way to facilitate communication. And essentially the whole idea for this week, in the whole ideas covered in this week was like introducing communication between the agents. If one can introduce communication between the agents, then as you may have seen during the lectures also, like we can do a lot more stuff than what we could have done without any communication between the players. So without any communication between the players, the only possible payoffs which we were able to achieve were the payoffs based on Nash equilibriums. But as you will see now, if we introduce communication between the players, like communication not during the play but a pre-play communication, like where before playing their turns, players just communicate beforehand. Even though that communication might be non-binding, like one communication can be signing a contract that if you do this, I'll do this, and like and the contract is supposed binding. Then that is one form of communication. Another form of pre-play communication is where uh, uh, players, even though they sign a contract, but they don't have to like actually follow the contract. But still, what this replay communication helps us in is introducing communication between the players. So even if a contract is non-binding, still what it can help us in is like if the two players can communicate before starting their turns, like they can toss a coin together and they can observe the outputs of a coin together and stuff. Whereas these kinds of things would not have been possible if there was no pre-play communication. Every player was playing on its own. But now you can have some kind of like correlated random variables between the two players also. And this is where this correlation terms comes into the picture. Because now both the players can have the same random seed for their actions or something. Whereas if you do not introduce any communication, then there's no random variable which is common between the players and their random variables are independent, then there is no correlation between their uh, random choices or their random seeds. So this is where just giving a high level picture of what was covered. So mainly this sharing of randomness or this correlation of randomness is what gives us uh, various new outlooks on the payoffs which can be achieved. So yeah. So just to see, so in correlated equilibrium, so in maybe we should just discuss this. So this is what I was saying previously, that there are payoffs achievable under Nash equilibrium, which are when you are not introducing any communication. Then there are payoffs which are achievable. Okay, maybe this should come first. Like, this is a better introduction then. Yeah. So for this guy, yeah. So initially, so this gives a better picture of what was discussed in this week. So till now we were discussing till last week's, or like till the week 10 at least, we were discussing payoffs achievable under Nash equilibriums, where we were not allowing any pre-play communication and every player plays uh, independently, like just trying to maximize what's best for them without knowing anything else or without any information. But now as we introduce communication, like we can go levels and levels, like there are the best payoffs which can be achieved are with communication and binding contracts. So these are what we discussed last week, which are binding contracts, where if a player signs a contract, then then the contract has to be enforced. And there are some things in between which I said that you can like you can introduce the concept of non-binding contracts also. Like even though players can sign the contract, but the contract may not be binding. And then one might think, what's the use of these non-binding contracts? Then the use is that this part, communication. Like even though contracts are non-binding, they can introduce communication between the players. and so now the players can share their random variables and stuff. So so in this also one can split it into two kinds of games. Some games where uh, one talks about okay, maybe we should go step by step hierarchically. So one was chaos achievable under Nash equilibrium, and then we also talk about chaos achievable with only direct communication. So right, what we said was okay, we are allowing communication between the players, but how are the players even communicating? Like there are multiple ways for players to communicate, right? Like there can be like the two players can communicate directly between each other. Like one Alice goes to Bob, and like they talk amongst each other that like let's toss a coin or let's play this and this together or something. Even though this communication is non-binding, like even though Alice and Bob communicate and let's say decide on playing 1-1, it's not necessary that both will indeed be playing 1-1. But actually, uh, uh, it was shown in the lectures also, and I think you can see this yourself also that uh, like there we and Alice Bob can design such schemes where even though the contracts may be non-binding or what they have decided on the communication may not be like enforceable, but it will be in their interest to actually follow through. Like there exist strategies or let's say there exists like these direct communications where it's where both Alice and Bob will actually follow what the direct communication says, even though there is nothing being enforced on them. Still, it will be in their interest to follow these. And uh, this was discussed in the week's lectures also that what kind of payoffs are achievable actually with only direct communication. It's just the convex it's just the convex hull of all possible Nash equilibriums. So so we know that without communication, the only payoffs which can be realized are the payoffs under Nash equilibrium. And then if you allow only direct communication, then actually the payoffs which are possible expand to actually a convex hull of these Nash equilibriums. So suppose like in Nash equilibrium there are some K strategies, then then any randomized strategy which is a convex combination of these K strategies can be realized using direct communication. And the proof for this is also quite simple because since we are taking convex combination of Nash equilibriums, uh, no player will have any incentive to deviate from that. Yeah. So payoffs achievable with only direct communication is just a convex hull of payoffs achievable at the Nash equilibrium. And then what we say is okay in payoffs achievable with only direct communication. What we are saying is uh, if the players are communicating directly, then both have the same information. Like if Alice is telling Bob something, then Alice knows that she has told Bob this, and Bob also knows what Alice has told her. So in direct communication, uh, even though the players are like communication can also be of two types, right? Here in direct communication, both know what is being said to each other. Like Alice knows what is being said to Bob, Bob knows what is being said to Alice. So this is what we call direct communication. But why just stop at this? One can also think, okay, like why are these two communicating directly? Uh, let's just think maybe there is a mediator between the two, and uh, so this is what we have like and this so like we relax this criteria a bit and we reach this part, which is like payoffs achievable with communication alone. So in communication we are talking about like in communication we talk about not just direct but also indirect communication. So indirect communication means that let's suppose there is a mediator present between Alice and Bob, and so earlier what was happening in direct communication was Alice and Bob, let's say if they toss a coin, then both observe the output of the coin and things like that. Whereas in a mediator setting, what happens is actually the mediator tosses the coin and individually tells Alice something that okay, like you should be doing this, and individually tells Bob that you should be doing this, without ever telling Alice and Bob actually what appeared on the coin or what appeared as the output of mediator's experiment. So essentially, in indirect communication, mediator talks to Alice and mediator talks to Bob. But Alice and Bob don't know what is being said to each other. Like in direct communication, Alice knew what is being said to Bob. Bob knew what is being said to Alice. In this kind of a setting, in indirect communication, Alice only knows what is being said to her, but does not know what is being said to Bob. Similarly, Bob only knows what is being said to him, but does not know what is being said to Alice. And uh, actually, this is actually even a more powerful tool than direct communication. And you can think of this like, why is this actually even a more powerful tool? Because direct communication is a special case where the informations are made public to both Alice and Bob. All the information is made public to Alice and Bob. But here in indirect communication, one can also hide some information from Alice and Bob. And there's some examples were discussed in the lectures also, where some payoffs were actually realized only because uh, Alice and Bob had imperfect information. If they had more information, if they had direct communication, then some payoffs were actually not realizable. So this is a strict so payoffs achievable with indirect communication is actually a superset of payoffs achievable with only direct communication. Okay. And this setting, as was discussed in the lecture, is one of the most common settings in real world also, payoffs achievable with communication alone. Suppose you're using Google Maps, then in Google Maps, like Google Maps is the mediator, and a lot of people are using Google Maps at the same time, right? So Google Map tells you that what path you should follow, but it does not tell you what paths are other following to the same destination. And that's why like Google Map can act as a mediator, and it's the job of the mediator to do a good job. Like a good mediator is someone like if you follow the mediator, if everyone follows what mediator says, then actually everyone is well off. So Google Maps service will be considered good when Google Maps is a good mediator, or that's which means that if Google Maps tells us, if even though Google Maps is suggesting different routes to everybody, but at the end everyone reaches efficiently at the final destination. Because if Google Maps suggests suppose the same path to everyone, then that road will get crowded, and yeah, then no one would be able to reach the destination on time. So chaos achievable communication alone require good mediator, and it's a superset. And as we said, uh, the chaos achievable communication and binding contracts is a superset of even this. Like binding contracts is like the using binding contracts, even though it's too powerful of a model, where we have to ensure like where we can be sure that if the agents have signed the contract, then they will be playing something. So these binding contracts are, even though they are very powerful, like in theory also, like you're enforcing players to like follow the contract. These are very powerful tools, and as you can see, like they are powerful, and hence uh, the set of payouts which can be realized using binding contracts is even a superset of payouts achievable with communication alone. And this can be thought of, why is this true? Because suppose here the contract is non-binding, right, in communication alone. So if the contract is non-binding, then if the contract was non-binding and suppose a player chose not to follow the contract, right? So that can be anyways enforced when we are using binding contracts. Like a player following a contract or not following a contract can anyways be ensured using binding contracts. Like if a player is not following, then you can just if a player is playing something in some kind of situation, you can just write that into the contract, that if this kind of a condition happens, then the player has to play this. So, or everything which can be achieved using indirect communication and non-binding contracts can be achieved using binding contracts also. Because whatever is being done in this case can just be written into the contract and be simulated as a binding contract also. And that's why like this is a very powerful tool. And in real world, yeah, there are cases where binding contracts are there, like in law binding contracts are enforceable. But like suppose Google Maps or something, these contracts are not enforceable. Like what Google Maps says to you, you really don't have to follow it. So now Google Maps cannot bind you, and then it has to be smart in designing its mediation strategies so that following Google Maps is the best way forward. And similarly, when we come this at a lower level in only direct communication, then again one has to design smarter strategies in direct communication so that it is in best interest of both the people to actually follow with what they had decided. And we know about chaos achievable and the Nash equilibrium, right? So this part where we can achieve payoffs using indirect communication is also called like correlated equilibrium. As you can wonder, as I gave the intuition also, like since players are communicating, they are sharing their random variables, and so there's a correlation between the random variables of the two players, and hence it's called correlated equilibrium. And its definition is quite simple. So a correlated equilibrium is an equilibrium where so it's basically a strategy suggested by the mediator such that for any player the payoff on the utility on following that strategy is actually greater than like that player playing any other strategy considering every other. So for player I, if player I thinks that every other player is actually following the mediator strategy, then the best action for I should also be following the mediator strategy itself. If this is true, then that's what we call correlated equilibrium. And as you can see, like what this ensures is that since every player wants to maximize their utility, this ensures that whatever the mediator is suggesting will actually be followed by each of the players. And like for this, like mediators need to design such strategies. Like it's not always clear like how will we obtain the correlate, how can correlated equilibrium be obtained, and but then it's the job of the mediator to be smart to be able to come up with such strategies. But we know that such strategies exist, right? And these kinds of things are called like if so this is the constraint which which should be like if this constraint is followed for every player, then only will all the players follow mediator strategy. And that's why like it's kind of an this constraint acts as an incentive for the players to follow what the mediator is saying. And that's why this constraint is also called like incentive compatibility. So incentive compatibility or like obedience constraint, that the players are actually obedient to the mediators even though they don't have to necessarily, but still because it's in their best interest actually to be obedient. Every player has the incentive to follow the mediator. So any suggested strategy of the mediator that satisfies this is called correlated equilibrium. So I guess the definition is pretty much clear. Then okay, maybe then one can come up with like okay, so after this like one can just model this mediated communication in Bayesian games also. So we had discussed what are Bayesian games. So in Bayesian games there were a set of agents, there were a set of strategies and a bunch of utility functions for those agents, but every agent also had a type, and this type for was not fixed for every agent, but rather it was chosen by nature. So for every agent, nature chooses some type T with some probability PT. Some probability distribution is initially given, and then every player is assigned some type with respect to this probability distribution. So now this type is something which is very private. Like only player I himself knows his or her type. Like, player I itself knows his or her type. No other player knows the type of I. So now this mediated communication. Suppose now again like there is this Google Maps, which is okay. Let's just take the example of Google Maps here also. So let's suppose like here the mediator is just giving an example of what mediated communication means in Bayesian games. So So for Google Maps, like earlier we said in correlated that Google Maps suggests you the path that you should take, right? And you are the player, and you choose to accept or reject the path, which the advice which Google Maps gives you, and so on. But where does this Bayesian games and this types come into the picture? So you can model this also into the Google Maps by thinking of it as this way that uh, your type is suppose the type of vehicle you are going in. So you can be going via uh, on like on foot, like you can be going to a destination on foot, you can be going on a two-wheeler, you can be going on a three-wheeler, or let's say a car, four-wheeler. So there are many ways in which you can go from a source to a destination. So suppose Google Maps also asks you that what's your type, like what here your type is actually the kind of vehicle in which you are going. And like this is also coming from a probability distribution, you can think, because like at some point like suppose due to some randomness because of some events you're going on foot, or there might be some probability that you're going by car, or there might be some probability you're going by bike, and so on. So yeah, so this is something which is chosen, your type, the mode by which you are going is chosen by nature, right? So here what the Google Maps is going to do is like ideal thing would be like in a road, it like maybe Google Maps will take into account like whether you're going on a two-wheeler, three-wheeler, four-wheeler, or on foot, and then suggest you a path accordingly. And this is usually what happens also on two-wheelers and four-wheelers, and on foot there are different paths suggested by Google Maps. But what you can do, so essentially what happens here is a mediator, which is a Google Map, asks each player for its type. So before suggesting the path to you, Google Map first asks for your type. It asks like, are you going on foot, are you going on bike, are you going on a four-wheeler and something. And uh, after that it's up to you to tell the Google Maps what is your type. But the main thing is you can lie also. Like even though I'm going by bike, I can say that I'm going by a car. What's stopping me from saying that? Or vice versa also. So I can lie also. So I can lie about my type, but whatever type I tell Google Maps that it is my type, and every person tells their types. So Google Map reads all these types and then recommends some actions to everyone. So after reading everyone's types, like all the people who are uh, subscribed to Google Maps, after reading everyone's types, Google Maps suggests everyone like what route should they be taking. And like yeah, and it tells with some like let's say probability distribution or something. But Google Maps suggests this keeping in mind the type which has been told to Google Maps. This type might not be the actual true type, but this is the type which has been told to Google Maps. This can be the misreported type also. And then utility for agent I can just be written as like this is just the expression for the utility of I when you take expectation over like types and the actions taken by the player I. Okay, so this is just equal to payoff under plan u, which is mu, which is the plan suggested by the Google Maps when players report the types truthfully. So so one can find out the payoff uh, under a plan mu, which is suggested by Google Maps, when players report the types truthfully, and PI knows TI. So PI knows like only the player I knows his or her type, right? So PI always knows TI, and if everyone follows the plan mu and everyone reports the type truthfully, then this is the payoff which one will get. But note that this payoff is maybe not optimal for someone. Like there might be incentive for a player to actually lie or misreport. And in how many ways can the player misreport? So in Bayesian games, like player can misreport to Google Maps in two ways, as I said. So first way is misreporting the type. So you can misreport that I'm not traveling actually via, even though you're traveling by a four-wheeler, you can say that I'm actually traveling by a two-wheeler and so on. So first way to misreport is your vehicle or your type. And then the second way to misreport or like deviate from the plan is by disobeying the recommendations. So note that Google Maps suggested So just keep this procedure in mind. Like first, you tell your type to the Google Maps. Then, so here it's up to you to tell the true type or not. Then Google Maps suggests some actions after keeping everyone after uh, taking in everyone's type and so on. Google Maps suggests some actions. And now again, it's up to you whether you want to follow the path suggested by Google Map or not. Since like it's not enforceable by Google Map by any means, it's a non-binding contract. So Google Map can only suggest. It's up to you to follow, right? So you can first of all misreport your type, and then whatever instruction the mediator gives you, you can also choose to not follow the instruction given by the mediator. So you can actually any player can misreport or like deviate in Bayesian games in these two ways. So now again, like what we talked in correlated equilibrium, good mediator will be someone uh, who's this utility when payoffs who suggests such plans. Like a good mediator will be someone who everyone actually follows and reports the truth. Like if the strategy of mediator is such that everyone is incentivized to tell the truth about their types and also obey them, then then that's considered a good mediator, and it will happen when like this payoff which we wrote here, which is payoff under plan mu when players report truthfully and pi knows ti. If this payoff is greater than uh, if this payoff for player I is greater than payoff for player I while doing anything else, like if the payoff for player I when reporting the type correctly and obeying the recommendation of Google Maps, if this payoff is greater than the payoff when the player misreports or disobeys the recommendations, then actually the player I will follow, will be truthful and also will be obedient to Google Maps or to the mediator. Since like player only cares about his maximizing his utility, so player will always like if the strategies by the mediators, if the strategy listed by the mediator is such that uh, player gets the highest payoff when he or she is being truthful and obedient, then player will choose to be truthful and obedient. Like players only try to game the system if they can earn, if they can earn more, or if the utility can increase. But if the utility is highest while being truthful, then why will the player, then there is no way player will be able to game the system or something. Okay, so that's what it comes to. Like, so as we define like this incentive compatibility or obedience in these correlated equilibriums, similar thing can be defined in Bayesian games also. So, and the definition is just the same. So incentive compatibility constraint is nothing but saying that uh, these constraints ensure that if this is not something uh, which will occur in all Bayesian games, but what we are saying is if this kind of a thing occurs, then that's what we call like a correlated equilibrium in Bayesian games, and a good mediator will be able to a good mediator strategies will be able to reach this equilibrium. And what are these constraints? So these incentive compatibility constraints are just that so like this can be compactly thought that uh, what's been written below, like the utility for a player I when he or she is being obedient and being truthful is actually greater than uh, the utility for player I when he or she is not being truthful or not being obedient. Okay, so this is the high level idea. Like even though this expression, you can just look at this expression and make mathematical sense out of it, but this is the high level thing which is going on. And this is what is called the correlated equilibrium of the Bayesian game. Like if this is satisfied for all players, then this is called like correlated equilibrium of Bayesian game. And like it can be thought that like again like this correlated equilibrium is attained if these are called incentive compatibility constraint. So if these incentive compatibility constraints are satisfied, then for all players, then it's called a correlated equilibrium in Bayesian games. So it's not too different from correlated games, but just one more level. Like in Bayesian games, there's two levels of communication. One is types, and then the second level is actually being obedient. Whereas in correlated equilibriums, it was just about being obedient or not. There was no issue concept of types. So actually, like incentive compatibility can be attained in Bayesian games also. Yeah. Once again, a person needs to be the once again here it can be achieved in Bayesian games, but the mediator has to be smart, and the strategies like not all strategies of the mediator will lead to correlated equilibriums, but there exist strategies which will give incentive compatibility constraints. So yeah, so mediators have to be smart about finding the strategies which satisfy these incentive compatibility constraints. Okay, so then so this is just I think a brief overview of incentive compatibility in Bayesian games, and then in the last, I think in the last 10 minutes of the lectures videos, there was this discussion around revelation principle. So revelation principle is okay. So on a high level, what is this revelation principle? So here we just talked about like communication between, in Bayesian games we talked about communication between mediator and the players, and the communication was first the player talked about his or her type, and then the mediator talked about the a plan. The mediator basically came up with a plan, and then it was like players' turn to actually follow the plan or not. So this can be generalized also, right? There can be multiple rounds of communication between players and mediators and so on. So this can actually be generalized, like and like the role of mediator is nothing but like you can actually do away with the mediator also. So you can just think about uh, players are communicating, let's say, within themselves. So let's say there are multiple rounds of players communicating between themselves, and but like there are no binding contracts right now. So this kind of situation is kind of complicated because players can communicate with themselves a lot, and how do you even model and get around all of this? So just the revelation principle, just at least I don't know the workings of it on the inside, but uh, it seems very at least the statement seems very clean and beautiful that Bayesian Nash equilibrium of these communication systems just correspond to a correlated equilibrium. So actually, all of these communication games and everything, you can just reduce these games to a game which consists of a mediator, and you have to find a correlated equilibrium. So even though there is no mediator here, everyone, all the players in the communication game, let's say, are communicating within themselves. Uh, but even then, all of this can be modeled as a correlated equilibrium. Basically, there exists a mediator who's talking to everyone, and then you have to find out actually the correlated equilibrium. So this is what revelation principle says. So actually, it kind of simplifies everything that's going on in an arbitrary communication system. Any players can communicate with anyone, but it simplifies to just every player talking to a mediator, the equilibrium of this game. So yeah, so this is to find out the equilibrium of this whole communication system. It might be difficult, and one might think what's all going on, but one can actually model this as a correlated equilibrium problem, and then we know how to handle correlated equilibriums, because correlated equilibrium just require this incentive compatibility. So yeah, so one way you can think, at least small example of this is this incentive compatibility in Bayesian, this Bayesian games itself. Bayesian games also consist of even though they're talking to a mediator, but they consist of some communication, right? The players are communicating with the mediator. Though there is no direct communication between the players, but here there is communication between the mediator and the players. And as we said, it kind of and it also almost reduced to the case of correlated equilibrium itself. We just had these compatibility constraints here also. Like in Bayesian games also we had these compatibility constraints, like we had in. Um, yeah. like we had in like correlated equilibriums. And revelation principle just says that this can be generalized to like any communication system where like players are communicating within themselves can be thought of as a system. Like to find the equilibrium of the system, one just needs to think of the system as a system which also contains a mediator and just find out the correlated equilibrium. So yeah, like like at least in theory, this looks like a very uh, beautiful statement because like modeling every all of this communication could be a bit complex, but one can just simplify this to a correlated equilibrium. Okay, okay, so Samsung has joined the meeting. So hello, Samsung. Are you able to hear me? Like, am I audible? You can type in chat. So just to maybe since you have joined the meeting, Samsung, maybe I'll just I'll give a brief recap of what I was discussing. So yeah, I was just discussing the high level ideas which were discussed in this week's lectures. So first of all, we I was talking about like actually what was the motivation behind this week's lectures. So initially, like till week 10, we were talking just about Nash equilibrium, but then we introduced some the concept of binding contracts, which allowed us to have multiple kinds of payoffs, and this was strictly stronger model than this Nash equilibrium model. But then we said, okay, like what if we allow communication, but we not allow contracts to be binding, like contracts can be non-binding. Whatever the players agree to, they might not play without any penalties. So then that's what is called payoffs achievable with communication alone. But note that this communication can also be of multiple forms. It can be direct communication or indirect communication. Direct communication means that both the players know exactly what is being communicated to the other person also. Whereas this indirect communication means that a player only knows what is being communicated to him or her. It does not know what is being communicated to the other person. So as can be seen, like this direct communication can be seen as a special case of this indirect communication, and so like the payoffs achievable under this model is a subset of this model. And the payoffs achievable with only direct communication is actually, as was discussed in the lecture, is actually just the convex hull of payoffs achievable under Nash equilibria. So Nash equilibria is when there is no pre-play communication. This is when there is pre-play communication, but just a direct communication. Okay. Then then I will discuss about the concept of correlated equilibrium. So correlated equilibrium concept usually exists in this kind of setting where we are talking about indirect communication between the players, so a communication with a mediator at hand. And we say that a mediator is a good mediator if all the players actually follow what the mediator is saying. Like all the players just want to maximize their utility, but like mediator has to design such a strategy that every player actually buys into mediator strategy to maximize his or her payoff. And this is what is like this constraint can be written mathematically also, that utility for any player when he or she buys into the mediator strategy is greater than equal to utility of that player if he or she deviates from mediator strategy. So utility is always better when so player has no incentive of deviating from mediator strategy. And this is also called incentive compatibility or obedience constraints, because the player is now being obedient to what the mediator is saying. And this kind of setting is called correlated equilibrium. Then we came to Bayesian games with mediated communication. Here, like we just added one more element to this correlated equilibrium, which was that like every player is initialized with a private type also, and this type is chosen by the nature with some probability distribution. So now mediator first has to ask each player for its type, and then each player responds truthfully or not truthfully. It's up to the player about his or her type. And then after reading everyone's type, which can be correct or incorrect, the mediator comes up with a plan. It comes up with a mediation plan. And then utility for any player can be written like this. So, and now what we want is every player to report the, and now it's up to every player to even be obedient to what the mediation plan is like. So there are two ways in which a player can deviate or like in these Bayesian games. Like first of all, player can misreport his or her type to the mediator in the first step. And then in the second way, which the player can deviate is whatever the mediation plan mediator is suggesting, he or she, the player disobeys the recommendation given by the mediator. And maybe these things can be helpful in the for like player a player will do these only if these kinds of things are helpful for the player to actually obtain some better utility. But it can be shown that there exists this concept of incentive compatibility in Bayesian games also. Like there existed obedience or incentive compatibility in correlated equilibrium. Here also these kinds of things exist. Like one can design like one can there always exists equilibrium of this form where these incentive compatibility constraints are satisfied for all players, which actually enforces that every player is like, if these kinds of strategies are designed by the mediator, then every player will be revealing his or her true type and will also be buying into the plan of the mediator. And then revelation principle just generalizes everything, generalizes this kind of Bayesian games and everything. And it says like any communication system between a bunch of players can be just modeled as a correlated equilibrium. So any Bayesian as equilibrium in this model uh, uh, can be thought of as a correlated equilibrium also. So yeah. Okay, okay. Samsung is, I think, left the meeting. But yeah. Okay then. So I guess these were the main concepts which were covered in this week's lectures. So since I believe we have discussed like all the high level ideas, then now we can come to the questions now. Okay, so I don't think discussing these questions will take a lot of time as most of the theory we have already discussed. So the first problem says that every correlated equilibrium is a mixed Nash equilibrium. So is this true or false? So actually, what we said initially was that like so correlated equilibrium comes in under this umbrella, right? Payoffs achievable with communication alone. So in indirect communication, like it can be seen that payoffs achievable in indirect communication is actually a superset of payoff achievable under Nash equilibrium. So here in Nash equilibrium, we consider both mixed as well as pure Nash equilibrium. So actually, payoff achievable in communication alone is a superset of payoff achievable under Nash equilibrium. And like one example is the prisoner's dilemma thing also. In prisoner's dilemma, which was discussed in the lecture, there was indirect ways with indirect communications where one could achieve some set of payoffs which were not achievable under Nash equilibrium. So actually, there exist examples where correlated equilibrium is not a mixed Nash equilibrium. So this statement is false. As the payoffs achievable under correlated equilibrium is a superset of payoffs achievable under mixed Nash equilibrium. So for an example, prisoner's dilemma. Just this was discussing the lectures. Like I won't be discussing it again. But you can just see it in the lectures itself. Right. So the answer to this is false. But the other thing would have been true that every mixed Nash equilibrium is a correlated equilibrium because like mixed Nash equilibrium is a subset of correlated equilibrium. So yeah. Okay then. Then uh, Then let's move on to the second question. Second question is a numerical based question, so I think it's a bit more fun, and it's similar to a question in the quiz also, so it will be helpful for you guys to go through this. So payoff. So this is a common data for questions 2 and 3. The payoff matrix for the game is given where both the players are maximizing their utilities. So this is the payoff matrix. So this is player two, column player is a player two, row player is a column is a player one. So the problem states that suppose the players find a mediator who chooses x belong to 1 to 3 with equal probabilities 1 by 3. So the mediator will choose x as 1, 2, or 3 with equal probabilities. This is what the players also know. Like players don't know exactly what x comes up with the mediators with the mediator, but the players still know like the experiment which mediator is going to perform. They don't know the output of the experiment, but they still know. Like this is what happens in indirect communication, that the players don't know the output of the experiment, but they still know the experiment that is going on. So and then whatever comes the value of x, mediator takes some actions or like gives some advice to the players. So if x equals to 1, mediator gives advice of p1 to play u, p2 to play l. If x equal to 2, it tells p1 to play d, p2 to play l. If x equal to 3, it tells p1 to play d, p2 to play r. So something like this. So this is something which, like this is the plan which all the players also know, but they don't know now like what comes up in the experiment of the mediator, right? So let's answer the questions based on the above problem. So maybe we can go option by option. So this is uh, so first option is if P2 hears L, it believes that P1 will play U and D with equal probability, and hence it will be optimal for P2 to play L. So note that if P2 hears L, like if the mediator tells, so what this means is P2 hears L means that mediator tells P2 to play L. So when is mediator going to tell P2 to play L? It's going to tell P2 to play L in these two cases. So either X, so if P2 equals, so if P2 hears L, then uh, P2 knows. So this gives P2 some partial information, and P2 now knows that X equal to either X equal to 1 or X equal to 2. X can't be equal to be 3 for in mediator's experiment, because if X was 3, then mediator would have told P2 to play R. So 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 P2 just knows that x equal to 1 or x equal to 2. And what are the probabilities for this x equal to 1 and x equal to 2? Uh, 1 and 2 occur with equal probabilities of 1 by 3. So now in conditional probabilities, like if only x equal to 1 or x equal to 2 is the subspace, then like both of these will be occurring with equal probabilities. Probability, that is, so the probability is 1 by 2. Okay. So now P2 does, even though P2 does not know the output of the experiment of the mediator, what P2 knows is that uh, x equal to either x equal to 1 or x equal to 2. Both are with probabilities half. So P2 will play accordingly. So P2 will assume that x equal to 1 or x equal to 2 came up, and both came up with equal probability half. And what this means is that this means that so So what does P2 believe? This means that P2 believes that if x was equal to 1, then P1 was being told to play U. And if x was equal to 2, then P1 was being told to play D. So, so this means that P1 actually plays uh, U with probability half. And D with probability half. So like since x is equal to 1 or x equal to 2 with equal probabilities, it means that P2 believes that P1 has been told to play U with probability half and P1 has been told to play D with probability half. And like P2 believes that if P1 does not deviate from the plan, then P2 will see whether it wants to deviate from the plan or not. So this means that P1 is playing U with probability half and D with probability half. And then P2 has to decide what it wants to play. Then expected payoff for P2 on playing. So P2 has two choices. P2 can play L or P2 can play R. So on playing L, what's the expected payoff for P2? So P2 believes like both of these events occur with equal probabilities of half and half. So if P2 plays L, then the payoff for P2 will be half times 1 plus half times 3. So it will be half times 1 plus 3, which is actually just equal to 2. And what's the expected payoff? Okay. Payoff for P2 on playing R. So if P2 plays R, again U and D are being played with equal probabilities. So on playing R, P2 gets a payoff of 0 here and 4 here. So it's half times 0 plus half times 4. So on playing R, the probability is half times 0 plus half times 4, which is again equals to 2. So payoff which P2 receives on playing either of L or R is actually equal to 2 itself. So what this means is that P2 can play actually anything. Like it is optimal. So P2 can play any linear combination of strategies L and R, and the payoff will remain 2 for P2. So P2 can play actually any strategy. Like it can choose to follow the advice also, and it's like it won't be harmful for P2 to follow the advice. Like the advice was to play L, so P2 can play L. So it is actually optimal for P2 to play L. Actually, it is optimal for P2 to play any mixed strategy. But yeah. And P1 will play U and D with equal probabilities, 0.5. This we already know, like because plays U with probability half and D with probability half. So yeah. So option A is correct. So it is optimal for P2 to play. Right. So option A is actually correct. Option A is correct. Let's come to option B. So option B says no. Why is it? Why is everything? I think now everything should be better. Yeah. So if P2 hears, okay, then the option B is if P2 hears R, it will play R. So let's see if P2 hears R, what happens. If P2 hears R, this means that there is only one way in which P2 can hear R, and P2 will know that like x equal to 3 was the output of the experiment, and which means that P1 was being told to play D. So P2 knows that P1 is being told to play D, and if P1 plays D, what's the optimal thing for P2 to play? It is indeed to play R, because if P2 plays L, then the payoff is 3, and here payoff is 4. So P2 will indeed play R if he hears R. So if P2 hears R, then he knows P1 hears D, and hence it is optimal for P2 to play R, because payoff on playing R when Okay, sorry for this guy. Because it is optimal for like P2 to play R if he's playing D, if P1 is playing D. Okay, and then so option B is also correct. So what's option C? So option C says that if P1 hears you, it will play you. So let's see, if P1 hears you, then this is the only way in which P1 hears you. This means that P1 knows that P2 will hear L. So if P2 is uh, playing L, then what's the best thing for P1 to play between D and U? On playing D, he gets a pair of 3, here he gets a pair of 4. So P1 will indeed be playing U because pair of 4 is more. So if P1 is being told to play U, then he will play U. So if P1 hears U, then he knows P2 hears L. And hence it is optimal for P1 to play U. Okay. Then maybe we can move to option D. Yeah. So option D says that if P1 hears D, it will play D. So again, if P1 hears D, then it can hear D in these two cases, and both these cases occur with equal probability, like in option A. So P2 will play L with probability half and R with probability half, right? So P2 will be playing L and R with probability half. Then what's the optimal strategy for P1 to play between U and D? Let's see. So if P1 plays U, what's the pair for P1? It's like half times 4 plus half times 0, which is 2. And on playing D, it's half times 3 plus half times 1, which is again 3 plus 4 by 2, which is 2. So both the times the payoff for P1 is 2. So P1 can actually play any strategy, any combination of strategies between U and D, and it will be optimal for him or her. Okay, so similar to option A, here it is optimal for P1 to play D. So actually it was optimal for P1 to play any other strategy also, but let's just say he chooses to follow. So it is optimal because it's not worse. So actually all the 4 options here are correct. Hence options A, B, C, D are correct. Maybe I'll just underline this so that you can see. So yeah. Now let's move on to the third question then. So third question is also again based on the previous question itself. So first option says that with the mediator in place, the expected payoffs are 2.5, 2.5. So actually we saw that with the mediator in place, like everyone was actually following what the mediator told them to, right? And what were the payoffs for everyone if they were like following mediator's plan? The payoff were actually 2, 2, not 2.5, 2.5. Like it can be seen by yourself also, like if U, L is played, it's played with probability 1 by 3. Similarly, D, L is played with probability 1 by 3. And D, R is played with probability 1 by 3. Note that like all of these are played because like we in the option A, we actually saw that everyone is being obedient to the mediator. So if U, L is being played with probability 1 by 3, let's see what P1's payoff is. So it's like 4. And then in D, L, the payoff is 3. So it's 4 plus 3. And then in D, R, it's 1. So the payoff for P1 is 4 plus 3 plus 1. It's like 8 divided by 3, which is actually not equal to. And similarly, like what will the payoff of player 2? For player 2, it will be again in u comma l, it will be 1. Then d comma l, it will be 3. So 1 plus 3. So it will be 4 plus 4, which is 8 by 3. So both the players get a payoff of 8 by 3. So it's not 2.5 comma 2.5, but rather something else. So let's do it option by option again. So as can be seen from the previous question, the players will indeed, like as you saw here, like whatever P1 hears, P2 hears, they will actually follow mediator. So will indeed follow the mediator or be obedient. Indeed be obedient to the mediator. So hence the and now if they are like obedient to the mediator, then this means that like both all these three things, if all these three scenarios occur with equal probabilities of 1 by 3, because x equal to 1, x equal to 2, x equal to 3 equal with the occur with equal probabilities. So hence the final output of the game is so 1 by 3 times. So I'm just writing the output in terms of strategy. So 1 by 3 times u comma l, 1 by 3 times d comma l, 1 by 3 times d comma r. 1 by 3 times u comma l plus 1 by 3 times d comma l plus 1 by 3 times d comma r. And what this means is just all these three states occur with probabilities 1 by 3, 1 by 3, 1 by 3. So, and what does this imply? This implies that like you can just calculate this yourself, that payoff for P1 is equal to payoff for P2, which we just discussed, which is just 1 by 3 times 1 plus 3 plus 4. 4 plus 3 plus 1. So 1 plus 3 plus 4, which is 8 by 3. So payoffs achieved, the expected payoffs are actually 8 by 3, comma 8 by 3, not 2.5, comma 2.5. Hence, option A is incorrect. Okay, then maybe we can move on to option B. So, okay, the option B says that the game without mediator has 3 mixed Nash equilibria. So I think you can try this yourself, like because we have discussed this quite a number of times about how to find out. Suppose now there is no mediator in the game, then one wants to find out how will the game end. So it will end at some of the Nash equilibria, and uh, you'll just have to see like what are the possible Nash equilibria here. So first of all, let's just rule out any. So I'll leave this as a like do homework exercise for you guys, because I think it's quite easy to do. Like we have discussed finding Nash equilibria in these kinds of games multiple times during this course, but just doing this orally, just to get an idea of what's to happen. So let's just see if there exists a Nash equilibrium pure strategies. So if this, let's just see if this is an Nash equilibria. Here it can be seen that player 2 does not have incentive to switch because his payoff reduces. Similarly, player 1 also does not have any incentive to switch because his payoff also reduces. So this is a pure Nash equilibria. This won't be a pure Nash equilibria. Uh, this won't be because player 1 will have incentive to switch, and this won't be. So there is just one pure Nash equilibria in this strategy, which is u comma l. Okay, and then to find out mixed Nash equilibria, in mixed Nash equilibria, one has to find out the set of probabilities such that the payoffs on playing, uh, like suppose like one has to find out a set of strategies for player 1, then you will have to assign some probabilities to L and R such that uh, uh, the expected payoff on playing U and D become equal if L and R are being played with some probability distribution, and similarly here. So I believe these kinds of things can be done by you guys yourself. So I'll just leave this as a do-it-yourself exercise. So first, like always, to find out all the Nash equilibria, note that a pure Nash equilibria is also a mixed Nash equilibria. So there are mixed Nash equilibria also. So again, let's come to option C. The chaos is associated with non-pure mixed strategy Nash equilibria without the mediator is 2.5, 2.5. So again, I leave this to you guys. Like, is this the mixed Nash equilibria? No. So maybe I'll just do it because it's not too hard to do. And then option D, D if D comma R is a Nash equilibria or not. Let's just see. Is D comma R a Nash equilibria? No, because like okay maybe yeah, it is not a Nash equilibria. Oh this is also an I think a pure Nash equilibria because player one does not have incentive to switch from 1 to 0. Similarly, player 2 does not have incentive to switch from 4 to 3. Oh, my bad. So this is also a pure strategy Nash equilibria. They are pure. These are the two pure strategy Nash equilibria, and yeah, and probably one Nash equilibria will exist in mixed strategies also, and probably so that's why this option will also be true. I don't know, like you have to calculate yourself, but I think this will be true. But like option D is certainly correct. So correct as can be seen from the payoff matrix, right? And option E is mediator strategy. With the mediator strategy, expected payoff of 10 by 3, 10 by 3, which is incorrect because we just saw that uh, payoffs are actually 8 by 3, 8 by 3. So as discussed in option. Okay. So option D is correct. I leave C and B to do it yourself for you guys. So for now, just option D is correct. Like these you have to find out yourself, and I won't be giving the final answer. Okay, then comes the fourth question. So fourth question says that every correlated strategy is binding. Is this true or false? So as we already discussed, like this concept of correlated strategies and everything uh, comes up in these kinds of things where payoffs are achievable with indirect communication. Here there is no binding contract. So actually pure strategies can be non-binding also. Like though it's another thing that in a correlated equilibrium, a correlated strategy actually becomes binding because of these incentive compatibility constraints. But in general, a correlated strategy is non-binding. A correlated strategy in a correlated equilibrium will be binding, but in general, it won't be. So yeah, false as discussed in the lectures. Yeah. So now let's come to the fifth question. It's again a true or false. So incentive compatibility essentially refers to offering the right amount of incentive to induce the truth revelation by the players. True or false? So again, like in this truth revelation or this revelation by the players of like reporting their true types, this is what is incentive compatibility, right? That one has to ensure these kinds of utility constraints so that actually player actually report their true types. So players will only report their true types if like the strategy is such that their utilities uh, are more when they report their true type. So this utility is this utility thing, like utility being better if they report their true types, can be thought of as an incentive. to report the truth. So yeah, so this is actually true. So this is a very fluid definition of like incentive compatibility, that like this right amount of incentive is a very fluid thing to say, which just means like the right amount of incentive is this, like ensuring this kind of a constraint is the right amount of incentive. Okay, so now let's move on to the sixth question. Sixth question says that in games with indirect communication, the players can see output of the experiments of the mediator. Is this true or false? So as we have already said that in games with indirect communication, like if the players could see the output of the experiments of the mediator, like for example in this question, if the players could see what x was actually equal to, like was x equal to 1 or was x equal to 2, the player can only see, like if P2 was told to play L, then he could only guess with probability half that it was x equal to 1, and with probability half it was x equal to 2. But if P2 was explicitly told that x is equal to 1, then P2 would have known that P1 is being told to play U, and then maybe it would have been better to for P2 to play something else, or like something and this like this can happen. Like for example, if P2 actually knew that x equal to 2, and then he knew that P1 was being told to play D, and then P2 would have actually not played L, but he would have played R because payoff on R is higher than L. So yeah, like so from this example itself, you can actually see that hiding information actually helps in achieving more kinds of payoffs. So yeah, so the information which we are hiding is precisely this, the output of the experiment. The players can only guess with some probabilities what the output of the experiment is, but they don't know the true output in indirect communication. But they know the exact output in direct communication. So if the question asks about just direct communication, then like players can actually see the output of the experiment. This is how, like, because like the mediator is then just no one as the players can just see directly the outputs of the experiments itself, and then can decide on their own the set of strategies which they want to see. This is incorrect. So this statement is precisely incorrect because indirect communication actually just means precisely this thing, that the players can't see the outputs of the experiment and just are being told individually on their own like what you have to do and what you have to do. So maybe not. It's false. As discussed in the lectures. So, yeah. Then maybe let's move on to the seventh question. So I'm not writing very long explanation for these questions because almost all the theory we have just discussed, and yeah, there's nothing really to it than just conceptual clarity. Seventh question says let A be the set of payoffs that are achievable under communication but no binding contracts, and B be the set of payoffs that are achievable under communication and binding contracts. So A is the set of payoffs achievable under communication but no binding contract, and B is under communication and binding contracts. As we told previously also that like there is a relation between the two, that like if there is no binding contract, then it can be modeled via actual binding contracts also. Like because you can just if a player chooses to actually follow the contract, then you can just have the contract as being binding. And if a player chooses to not follow the contract, then it can be thought of as a contract. Then you can just put this in the contract itself that the player will not be following this. So this is the high level idea. And so like yeah, as discussed here also, that communication and binding contracts gives us more leeway than just communication alone. Okay, so yeah, so if basically a contract is not followed, then it can just be thought of as not being a contract at all. And if it is followed, then it can be thought of as being a binding contract actually. And that's why yeah, the set of binding contracts is actually a superset of the pairs achievable under binding contracts is superset of pairs achieved under non-binding contract. So actually this statement is incorrect, and actual statement should be like, so A is not equal to B, but actually B is a superset of A. So this statement is actually false, as discussed in the lectures and also discussed previously, right? So yeah, and then just a bunch of more theories like questions. So yeah, so like I gave the example of Google Maps or real estate brokers. These examples were given in the lectures also. So Google Maps or real estate brokers facilitate indirect communication between their users. Is this true or false? So it can be thought of that actually this statement is true, because like as I said that Google Maps is actually acting as a mediator, and hence like forms an indirect communication between different people who are using, because everyone is just being told what they have to do, but it does not mean that they tell but we don't know like what others are being told who are following the same road. Like, are others also being told to follow the same road or some other road? And similarly, in real estate, also, as was discussed in the lectures, it might be possible that a real estate broker tells you to buy some house in some place, whereas he tells some other person to buy a house in some other area, and they might do this not ill intentionally or something, but because like these strategies may be optimal for both the players. Like, the utility for both the players may increase if the real estate brokers choose to do this. Because like suppose there were two societies, and uh, like in both societies, like two flats were empty, or yeah, two flats were empty, but both flats were very close. So if a person lives in one of the flats, like so there are four flats in two societies. Like, so society A has flats, uh, flat 1, flat 2. So basically 1A and 2A are the flats in society A, and flats 1B and 2B are the flats in society B. But 1A and 2A are very close to each other, and 1B and 2B are very close to each other. So any person residing in flat 1A will want no other person to move into flat 2A. Similarly, any person residing in flat 1B will not want any other person to come into flat 2B. So what the real estate broker might do is he might tell independently one person to move into flat A, 1A, and the other to move into flat 1B. So yeah, so this kind of indirect communication is being facilitated using real estate brokers, and it might be to increase the overall utilities for everyone. So something like that. So this is true. Indirect communications are suggesting different things to different people is not like is not Google Maps or real estate brokers being biased. They are just acting as mediators, and mediators try to find these set of strategies which have these kinds of incentive compatibility constraints. So they want everyone to be incentive compatible, and that's why they might suggest different things to everyone. It's not out of ill intention or something always. So just one thing to maybe think about. Okay, so this is the last question for the day now. So the last question for the day is, and like probably the last question for these problem solving sessions, because tomorrow we won't be discussing any questions, but we'll just be discussing summary of everything which we have covered. So this ninth question says that in indirect communication, obeying the strategy recommended by the mediator is optimal for a player, even if the player has complete information about what has been recommended to other players. So it says that in indirect communication, obeying the strategy recommended by the mediator is optimal for a player, even if the player has complete information about what has been recommended to other players. Okay. So note that in indirect communication, usually a player does not have complete information about what has been recommended to the players. It only knows about what has been recommended to himself, right? But here we are saying, like, even if we consider that the player knows everything, like what has been recommended to other players, which essentially means that the player knows about the direct communication. Like, this communication is actually not indirect, but actually indirect communication for that player. Even then, the obeying the strategy by the mediator is optimal. So note that this is like, okay, like, so nevertheless, like, it's not always necessary for a strategy recommended by the mediator to be optimal for a player. But suppose the strategy in the indirect game was actually optimal for everyone, like it had incentive compatibility constraints, but now suddenly some person comes and gives the player all the information about the mediator. Maybe I should reformulate this question. Okay, suppose the mediator has incentive compatible strategy S. SI. Okay, player I. So strategy SI is like incentive compatible strategy for the player I. Uh, suppose someone comes and say, suppose some adversary maybe comes and gives complete information to player I about what has been recommended to other players. So initially, there is an incentive compatible strategy for the player I by the mediator. So right now everything is fine. Like everyone, like, so as a player I will be following the strategy SI in indirect communication because like it's an incentive compatible strategy. But now suppose suddenly some adversary comes to player I and gives complete information about what has been recommended to other players. So suddenly, what happens is an adversary. So right now, everyone is fine. Like player I is fine with playing strategy SI as it's optimal for him or her. But suddenly, an adversary comes up and tells the player I about some further information. Like he tells the player I about, okay, like the other players have been told such and such strategies by the mediator. So this adversary is playing uh, like, yeah, this is an adversary, so yeah, it's giving now complete information rather than like a partial information which was given by the mediator. So now the question is, will it still be optimal for player I to play the strategy SI? So here what we are saying is, now every, like, the player now, like, even if the player I comes to know about the strategies which have been recommended to other players by the mediator, will it still be optimal for player I to play this strategy SI itself? Or maybe, yeah, maybe will the player I deviate from the strategy SI? Yeah. So if the player I comes to know about what has been recommended to other players by the mediator, will the player I now deviate from the strategy? So will the player SI still continue to play the strategy SI, or can the player deviate from the strategy SI? So actually the answer is like true that the player can. Yes, the player I can deviate from the strategy SI now. And why is this? Because uh, like this is because now like player I has now some more information. It now knows like what has been recommended to other players, so he can change his plans uh, accordingly. Like if he knows now like what has been recommended to other players, like earlier it could have only guessed with some probabilities like what could have been recommended to other players, but now he precisely knows what has been recommended to other players. So now he can precisely formulate a strategy which maximizes his utility with respect to what has been recommended to other players. Previously, he could have only guessed, and so he could have only optimized with respect to those guesses. But now he knows precisely, and so he'll find out a strategy uh, with respect to this updated information. Now, as more information, and hence we'll try to optimize his utility further. So player will try to optimize his utility further after knowing that after knowing that this has been recommended. And this is an example which we saw here also, right? Which I was saying here also. Suppose this is the problem, and like everything was chosen with equal probability 1/3, and like this was being players were being obedient with respect to this mediator strategy. This is what we discussed in the second question, in this question. But suddenly suppose uh, someone comes up and tells the output, like suppose the output was x equal to 2, and just an adversary comes up and tells to uh, the player uh, the player 2 that the output of the experiment was actually 2. So some adversary comes up and tells the player 2 that the output of the experiment is actually 2. Then the player 2 knows that P1 has been told to play D, and so player 2, instead of choosing to play L, will instead choose to play R now. Because in R, the payoff of player 2 is 4, and here the payoff is 3. So if x equal to 2, P1 player 2 comes to precisely know that x equal to 2, he does not have to guess between x equal to 1 and x equal to 2. He precisely knows that x equal to 2, then he knows that P1 has been told to play D, and so he will choose to play R. Because on playing D, like on playing L, like payoff is 3, on playing R, payoff is 4. So actually here you can see an example where player on getting more information actually changes his strategy for a better utility. So note that on changing the strategy, utility of the player can only increase, like, because he otherwise had this strategy itself. So why will he choose another strategy which decreases his utility further than this? But just giving a high level idea of what's going on. So answer is yes. As he more information, will try to optimize his utility further. So note that here, like now as the player I is deviating, if only player I is deviating, then his payoff will also be increasing. Like note that it's not just that his like the player's I payoff will also be increasing because uh, his utility is being further optimized. he otherwise, like, why will he choose to not follow the advice given by the mediator? Like, he only has an incentive to not follow the advice given by the mediator if using the full information he can optimize his utility further. So yeah, something like that. So the answer to this is yes. Okay, so okay, then I guess this was the last question for the day, and probably the last question from my side for this course. So I guess yeah, since no one is present in the session in person, uh, like no one can ask the doubts in person, so maybe I'll just stop sharing. And yeah, hopefully, just as a reminder to everyone who's watching on YouTube that there is a session scheduled tomorrow also from on Tuesday, like 6 to 7 p.m. It's just a 1 hour session, and it will be a summary session. Like there will be uh, discussing not any questions, but rather just the high level topics which were discussed in the overview of topics which were discussed in the course. So that can sort of act as a revision for you guys. Okay, then. So hopefully I'll see you guys in person tomorrow in on Tuesday, like 6 to 7 p.m. So till then, thanks for watching, guys, and goodbye. I'll just be stopping the recording.